All right, so k-means clustering is an old, very simple technique, very effective. It works if you have data that has clusters. So we're going to make data that's just, Gaussian blobs. So here we are. We got two big blobs and three little blobs of x1 and x2. And we want to separate these into categories. And the k-means model is incredibly simple. You run the k-means model. It will just start with, I think, yeah, this is the result of running the k-means model. You see, it found centers of these 5 points and it found boundaries between them very nicely. So this is a good result. Now we're going to see how it works. And we're going to print the algorithm one by one. So here is how it started. First, it just randomly places the centroids. Then it labels the instances. So you put a centroid here, so it takes all the dots that are closer to that than any other centroid. All you do is take this distance and cut it in half. So it took these and put them in that category. Now you move this centroid to the center of those labeled dots. So it moves over a little. Now, when you insert the points, these points here that really aren't in that cluster are now largely no longer included in the cluster. Only a few of them are. So next time you move it over, it's going to get better until you get pretty good after just a few iterations. Like I say, this is just like putting a heavy object on a trampoline. And the point is, this works extremely fast. It's extremely simple. And as you can see, it can work. The problem is, if you get a bad start, it can go wrong. So if you end up with a starting value like this, now you label them. It's going to split this one in half and put half of them there and half of them there. It's going to be confused about this. It's going to try to split this in half and put half up there and half down there. And once it's off to such a bad start, it will never succeed in escaping this. It's determined to split this into two clusters. And there are a lot of dots close to the centers, so it's never going to decide that's wrong. This is a mess. It's never going to be able to fix that. You're going to end up with this, splitting one in half and merging these two into one. That's what can happen. So in practice, what you do is you run it 10 times. And then you take the most popular answer because these failure cases are relatively rare. And there's another problem. If you make the vertical axis bigger, then it's going to weight errors in the vertical direction far more than errors in the horizontal direction. And you'll get a really bad fit like this because it's not willing to put a center here and accept an equal amount of error, vertical and horizontal. The vertical errors count much more. So it is entirely unwilling to believe that these dots belong in this cluster. It's better to put them in this cluster with a much greater horizontal error. So the model is not failing at all. It's doing what you told it to do because you didn't pay attention to the scaling. You gave it the wrong instructions. You told it to minimize the distance on this kind of scale, and that is the solution that minimizes the distance you told it to minimize, kind of thing that can happen to you. So now if you make a moon-shaped database here, the problem is it really only is good for finding clusters that are round. That's what it's designed for. But in my opinion, this is a pretty good solution. It sorts them into categories, and then you'd say these four are one group and those four are another group. Now, the textbook I got this from said this is a bad fit. It didn't sort them into two groups. And I say, well, yeah, but it did sort them into categories, which could be easily used to determine those groups. But anyway, that's an issue. And now, this was really impressed me. This is what I mentioned in our first lecture, semi-supervised learning. This really works. So here, we're going to take a digits data set with 1,700 images of handwritten digits looking like this. Okay. And we have the answers down here. We know the labels, but we're going to, so we fed them all to the training set the usual way, fitting the entire 1,400 images with labels. We fit a model, and the end result is it's 90.68% accurate. Okay. So that's what happens if you have all the labels. Now imagine we didn't have labels for this data, and we're trying to learn anyway. Now you could try to model to just 50 instances. Suppose I only have enough energy to get humans to label 50 of them. Well, if I train on 50 instead of all 1,400, then I only get 74% accurate, not 90% accurate, as you would expect. I have a much smaller sample. I'm more likely to learn bad habits from the various, I might only have a few samples of a one. They might all be slanted the same way. So it gets the wrong idea of what the right shape of a one is. So now what you do instead of that is you run a k-means model to form 50 clusters. You find the clusters, and then you find the images close to the center of each cluster. So now instead of choosing 50 random instances to label, I've chosen 50 representative images. Each of these are right in the center of a cluster of similar images. So now I label these by hand and interpret the whole cluster as having that label. And the end result of that is I get up to 84% accuracy. Now, the next thing is, remember what happened up here? The clusters sometimes include things that are pretty far from the center. Even if I get a good solution like this, I've got things out here that really are pretty far from the center of that cluster. So taking the label here and applying it up there, that might be wrong. So it would be better than simply applying the representative label to the whole group would be to remove the outliers. So we find the 1% of the instances that are furthest from the centroids and we just throw them away. We don't use them because we're not really sure what the label should be. And we don't want to try to pay a human to label them. So if you do that, if you clean up the data by removing the outliers, now you get 90.9%, which is better than the original model trained on all the labeled data. So that's why I say this is, in fact, a very powerful technique. All right. And so that's what I wanted to show you about k-means, what you can do with no labels, and how you can compensate for having no labels.